Hi, I'm Brooke Bobo, and this is my video explaining the mechanism for Week 8 of Organic Chemistry 2 for the University of New England Online. So this was the reaction that I was given for this assignment, and when I was looking at it to try to figure out where to start with this mechanism, I realized that this reaction is a Dieckmann condensation, which is pretty much the same thing as a Claisen reaction, but instead of being two different molecules, it's just an intermolecular condensation, which is what we can see here because we go from two, ester groups to one ester group and then a ring that has been formed. So that kind of made me realize that. And then right here, as you can see, this beta hydrogen right here, it's not shown in this image because this is just what I was given on the worksheet, but it's drawn in on the next slide. And this beta hydrogen that would be right here is the electrophile in this reaction, and sodium ethoxide right here is the nucleophile. So the first thing that happens in this mechanism is that the sodium ethoxide nucleophile comes in and will attack this beta hydrogen of the carbonyl carbon on the right, which is our electrophile, like I said. Then the electrons from the beta hydrogen bond are kicked off to form a double bond right here to the carbonyl carbon, which then kicks off the pi bond from the carbonyl carbon and makes it attached to a negatively charged oxygen rather than that carbonyl that we see when this reaction starts. So then in the next step, that negatively charged oxygen that we just formed is trying to get itself to be neutral again. So one of these lone pairs on the oxygen reforms the pi bond that was broken in the last step. So then the new pi bond that was formed right here will reach out for the partially positive carbonyl carbon on the other side and will form a bond between these two carbons. And as a result of that, the pi bond of the carbonyl carbon on the other side will get kicked up onto the oxygen as a lone pair, like we saw in the last step. Then for step 3, this negatively charged oxygen on the other side is also trying to get itself back to its neutral state. So it's going to reform the pi bond right there like this, and then this ethoxide group becomes a leaving group. So it leaves the main molecule right here, taking the electrons that it was attached to with it. After that, the negatively charged ethoxide that we took off of the main molecule in the last step right here will then come back to try to neutralize itself by taking a beta hydrogen from the carbonyl carbon on the right again, just like the way this reaction started. It will take this beta hydrogen, and then the electrons that was attaching the beta hydrogen will move to make a pi bond next to the carbonyl carbon. And as a result, the pi bond of the carbonyl carbon breaks, and then its electrons transfer onto the oxygen, forming another negatively charged oxygen, which is obviously not what this molecule wants to be. Then after that, the negatively charged oxygen is once again trying to neutralize itself. So it's going to reform the pi bond, and as a result, the pi bond of the ring will grab a hydrogen back from the acidic workup that was stated in the instructions to this assignment, and then it's going to try to overall neutralize this molecule again. Finally, as seen in the very first slide, we reach our end product, which is a cyclic molecule right here. And then this is the overall mechanism. Throughout this video, I've just broken it down step by step, like this is the first step, second step, third step, fourth step, and fifth step, leading to our final product that we just saw. But this is an overall description of the electron flow throughout the mechanism. I put the charge of each intermediate next to it, so as you can see, all of the intermediates have a negative charge. Right here, it's on the ethoxide, right here, it's on this oxygen, then it moves to this oxygen, then after that, it's on the ethoxide again. It's kind of hidden behind me, but you can see it in the previous slides. And then here it's on this oxygen again. And finally at the end, we lead to a neutral molecule. So all these intermediates have this negative charge, which is kind of the driving force beyond the whole behind the whole reaction, because the goal is to have a neutral molecule in the end, just like the neutral molecule that we started with in the beginning. But this time the ethoxide is neutralized again. So basically the whole point of this is just to try to neutralize the whole molecule. Finally, the stereochemical preferences. So in this particular reaction, like the one I was given, there are no stereochemical preferences because the sodium ethoxide is not a strong base. Sodium ethoxide is considered a weak base, so it's not going to give any kind of preference for the stereochemistry or the regiochemistry, because also this molecule was pretty symmetrical. But if there was a different strong base to use, then the less substituted beta carbon would be deprotonated, which would have been the other side on our molecule.